Okay. Hello everyone again. So in this video, we'll talk about hypothesis testing for mean when sigma is unknown. Okay. So remember, up to now, we were testing this hypothesis, this type of hypothesis, mu is equal to 70 versus h1 mu is not equal to 70. Okay, and we said, well, sigma is given and it's something like 8.9. Okay, so up to now, we assume that sigma is given. Now, we will relax this assumption and try to see what happens, what can we do when sigma is not given. Okay, so now we have so we will talk about the t distribution. Okay, well, the central limit theorem, okay, that's nice, but well, but when you are using central limit theorem, remember when we are using the hypothesis testing. So let's go back. We said that the observed is equal to x bar minus mu divided by sigma divided by root n. So x bar is the data that we are calculating. We have calculated. Mu is given by the null hypothesis h0. We know n, okay, that's great. But however, sigma, okay, sigma is given in the question, okay, but most of the time we don't know sigma. So since sigma is given, we can just write and see that this is approximately normal. But if sigma is not given, then if you don't know sigma, then you're not able to write this one, okay? Um, so what you can do is just think a little bit, just pause the video and try to think, well, what happens if you don't know sigma? Okay, so now you think about this. So what you can do is, instead of sigma, since you don't know sigma, you can just use the point estimator of that one, okay, which is s. So you can just write x bar minus mu divided by s divided by root n. That's great, you can write this, but now it's no more z. It's no more z because in z, we know we have to know mu and sigma, but now we don't know sigma. Hence, this is no more z, but this is what we call a t distribution. Okay, so this is another random variable. Okay, this is another random variable, which is called t random variable. Okay, um, okay. So, well, if x bar, so let's read the definition. If x1 dot 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 x and be independent random variables that are all normal, this is important, okay? All normal with mean mu and standard deviation sigma. And let's define x bar as the sample mean and s square as the sample standard sample variance. Then x bar minus mu divided by s divided by root n is a t distribution with v equal to n minus 1 degrees of freedom. So recall for z, do we have any parameters? So what does it mean? So do we need anything to just make the plot of the normal, the standard normal, and so that we can calculate the probability? Well, no. So the standard normal has a distribution just like this, okay? Without knowing any parameter, you can just plot this because, well, it's already given. But for t distribution, we have a parameter, which is the degrees of freedom. Once the degrees of freedom is given, you can just plot the t distribution. So, well, the t distribution is very, very similar to the normal distribution. So this part, this blue part, right? This blue part is the plot of the t distribution with 2 degrees of freedom. This black part is the t distribution with 5 degrees of freedom, okay? And the upper part, okay? Let me just make green. So this part, this green part, okay, this green part, that's the one with infinitely many degrees of freedom. In fact, when t degrees of freedom, t, the random variable, has the infinite degrees of freedom, then this is equivalent to the standard normal, okay? Well, once you know this t distribution, the whole procedure is the same. How? What you will do is, okay, remember our standard normal. We have this standard normal. We are just leaving an area of alpha over 2 to the right, alpha over 2 to the left. And as remember, we call z alpha over 2 here. And this is minus z alpha over 2, okay? We will do exactly the same thing. Okay, sorry for this. We will do exactly the same thing. How? Now we will make a standard, not standard normal, but we will make the plot of a t distribution, and it will be t alpha over 2, okay, with v degrees of freedom, and this will be minus t alpha over 2 because it's symmetric as well with v degrees of freedom, which leaves an area of alpha over 2 to the right and alpha over 2 to the left, and just proceed exactly as we did in the standard normal case. Well, this is the table for the t distribution, okay? Remember, for normal distribution, this was the table for normal distribution, okay? So in the normal distribution, you have this table, and these values in the table show you the probability. Remember, what was this? 0.0006. So this is the probability that z is smaller than minus 2.22, okay? So 2.20 comes from here, 0.2 comes from here. So this is minus 3.22 is equal to 0.0006, okay? Or let me just pick this one. Let me just pick this one, okay? So what is this? Remember, this is can be written probability that z is smaller than what? Minus 2.34, okay? Why is that? Because I have this. This, right? That's equal to 0.0096. Okay. So in the z table, these values are the probabilities, which is this area. Okay. So you are just given probability that is smaller than the value that is given the rows and columns. So in T table, it's a little bit different. How? Now, the table just gives you the area. So the table just gives you not the probabilities, okay? So just look at here, for example. Let me just see. Look at here. Let's look at here. So this is 1.476. This is not a probability, obviously, right? Because if it's a probability, then it should be smaller than 1. Hence, this table is different than the others. How can we read this 1.476? So this table just gives you, so this part, the inner side, so this side, just gives you what? This gives you, well, the t values, the t alpha values. Alpha values are here, and these are the degrees of freedom, okay? This is because in normal distribution, standard normal, you don't have any parameter, but here you have a parameter. So let's try to write this. Let's try to write this one. How? This is, let's write this. This is probability that t random variable with 5 degrees of freedom. Okay, let's say this is probability t so that v is equal to 5. Later, we will drop this notation because in the question, the degrees of freedom is given. Hence, I won't use the degrees of freedom in the questions. Here, since we will solve different t random variables with different degrees of freedom, I will keep this. Probability that t random variable with 5 degrees of freedom greater than 1.476, that's equal to what? 0.10, okay? It comes from here, 0.10, right? And this 5 degrees of freedom, it just comes from where? It just comes from here. And how about this? It just comes from here, okay? Or let's solve this one. Let's try to see what is this. This is equal to, let me just write it with a different color. This is probability that t random variable with what 9 degrees of freedom is greater than what 1.1 is equal to 0.15. Okay, so this is how you read the table. So well, So just look at this one, 1.476. What is this? This is the t random variable, okay, that leaves an area of what? That leaves an area of 0.10 to the right, okay? So this is t sub 0.10, but where at b is equal to 5 degrees of freedom, okay? How about this? This is the t random variable, which leaves an area of what? 0.15 to the right, okay? At which degrees of freedom v is equal to 9 degrees of freedom, okay? So this is how you should just read the t distribution table. We will solve some questions in the recitation hour as well. So now this is the t distribution, and this is how to read the t distribution. Now, so what is the hypothesis testing for mu when sigma is unknown? Well, the hypothesis remains the same. So what you do is you just check whether mu is equal to some value. So mu zero means that, well, this is a scalar, just like, I don't know, 70, 150, minus 3, and so on and so forth, okay? So the hypothesis is the same. Now the test statistic is so let's say this is the value of the test statistic, okay? The value of the test statistic, The value of the test statistic is given by t observed, that's equal to x bar minus mu. So in fact, this is x bar observed, okay? Sorry. So this is x bar observed, minus mu 0 divided by s divided by root n. Hence, the test statistic is what? The test statistic is, of course, is the t random variable with what? B is equal to n minus 1 degrees of freedom. Hence, the test statistic, the value of the observed test statistic is given by this, okay? So for any given alpha, what we will do is for any given alpha, what we will do is find the t alpha, okay? Find the t alpha over 2, then find the observed t value, t observed, and check whether the t observed in the critical region, that is, check whether t observed is greater than t alpha over 2 value, or it is smaller than minus t alpha over 2 value. If it is in the critical region, then we just reject the null hypothesis. So remember our hypothesis testing, the steps for hypothesis testing. So the first step is state the null and the alternative hypothesis is the same. Well, H0 mu is equal to 70 versus mu is not equal to 70, okay? Of course, this is a particular example. It's not always 70. Choose an appropriate test statistic. For this case, since sigma is unknown, we just choose T, where the degrees of freedom is equal to n minus 1. Establish the critical region. The critical region in this case is equal to R minus, so this is T alpha over 2 minus T alpha over 2, T alpha over 2, okay? So this region is your critical region. Calculate your test statistics observed value, which is T observed. So T observed is equal to X bar observed, your observed X bar minus what? Minus mu. So this mu comes from where? H0, right? You assume that H0 is true. Divided by S divided by root n, okay? Well, reject H0 if the computed test statistic is in the critical region, okay, if it is in here. Otherwise, do not reject the hypothesis, okay? So let's make an example. Well, we have the students, the height of 10 students from, let's say, this class, okay? So these are the heights. Well, what I want to do is I just want to make hypothesis test, okay? Okay, so sorry for this. In fact, this is this slide should be before. Hmm, hmm, Okay, that's correct. Okay, sorry for the delay. So we have the heights of 10 students from this class. Okay, so what you can do is you can just find the x bar of this class and s square or S square or S of this class. Okay, so it turns out that, well, the X bar is equal to 167, and S is equal to the sample standard deviation is equal to 8.87. Okay, so what I want to do is just test whether the mean of the students in this university is equal to 170 or it's not at a significance level of 0.05. Okay, so since, well, so you can just make this as the 5-step procedure. Okay, so step one, let's say step one, well, H0 is mu is equal to 170 versus H1, which is mu is not equal to 170, right? So step two, just choose your test statistic. Well, it's not X bar, it's not Z because you don't know sigma, right? You don't know the unknown parameter of the population, so you only know S. So what you can use is the T distribution with how many degrees of freedom? V is equal to n minus 1, which is n minus 1, 9 degrees of freedom, okay? S3, just find your critical region. Just find T sub 0.025. Okay, let me just write for now, but we will later omit this V. V at 9 degrees of freedom, okay? So in fact, we can just go and, where? We can just go back, not this one. So just look at here, 9 degrees of freedom, 9 degrees of freedom. So what is the alpha value? Alpha value was 0.025, was it? No, it was 0.025, right? 0.025. So it's not here. Let me check. Do we have it here? It's here. Okay. So again, 9 degrees of freedom, alpha value of 0.025. That's equal to what? 2.262. So how to write this? Okay. How to write this? So this is equal to, let me just write it here. So the probability that the t random variable with how many degrees of freedom is equal to 9 degrees of freedom, okay? So greater than 2.62, 2.262, okay? That's equal to what? 0.025, right? And this is simply t sub 0.025. Okay, that's great. So this is my, hmm, oh, it's already given here. Okay, so uh, rejection region is my rejection region is real numbers minus 2.262 and 2.262. Okay, this is my rejection region. Or as I said, there is nothing called acceptance, but we may write acceptance region. Okay, so this is the region where you don't reject the null hypothesis. Um, okay, so this is not step 4. Sorry for this. So this is the rejection region. Now, sorry. Okay, now let's make step 4. Step 4 is find the observed t statistic. Step 4 is t observed. Okay, so t observed is, just look at here, x bar minus mu 0 divided by s divided by root n. So this is x bar minus mu 0, which comes from the null hypothesis, divided by s divided by root n, which is equal to minus 1.069. Okay, so which is inside the acceptance region or outside the rejection region. Hence, this is what? This is step 5. In step 5, we don't reject the hypothesis. Okay, don't reject. Okay, don't reject it. Great. Okay.